Good afternoon, everyone. So I welcome you all on behalf of the entire mechanics teaching team to the special class sessions of mechanics. So I hope all of you are staying safe. So this you all probably know that I am Chakraborty of Mechanical Engineering Department, and although I teach only the sections of 3 and 4 in the usual times, but the plan is that this lecture will be broadcasted and it is meant for all the 10 sections, sections 1 to 10. The plan is like this, that so different sections have covered different amounts of material, and going forward what we will do is we have estimated a common ground and we will try to build on that so that everyone can move forward together. So the first lesson plan is like this, that more or less we have found out that the content covering the tutorial sheets 6 and 7 have been more or less covered. Now the next is tutorial sheet number 8, and the material corresponding to that is transformation of stresses, Morse circle, principal stresses and pressure vessels. So towards that end we will try to cover these topics as soon as possible, but before we can actually launch into transformation of stresses, we have to recap the concept of state of stress at a point. So the first order of business will be to discuss this very important topic. So first up, so again I emphasize that once we have briefly discussed this very important topic, we can actually make a headway into the actual syllabus topic of transformation of stresses. So for state of stress at a point, what we will do is we will first consider a general 3-dimensional body. So I will depict the body in this fashion, some kind of arbitrary shape. So this is a general 3-dimensional body, and we will represent the coordinate axis in this fashion. This will be our x, our y and z. Okay. Now as the topic says, we are going to consider the state of stress at a point. So the point of concern for our situation is this generic point Q within the body. So this point Q is not lying on the surface of the body, rather it is lying somewhere within the body. Now we want to investigate the state of stress at a point, and we would like to discuss what this state of stress even means. So first of all, what we are going to do, in order to investigate the point Q, we are going to expose the point Q from within the body, and the way to do it is through a thought process of cutting it by an imaginary plane. Now this imaginary plane, for the purpose of our discussion, would be specially chosen to be parallel to the YZ plane. This is our Y axis, this is our Z axis, so our plane would be somewhat like this. So this is our plane which is parallel to the YZ plane. This plane has been chosen in such a fashion that it is passing through this point Q. Now as a result of this cutting plane, what we will have is that what I want to do is I want to isolate the left hand side part of this 3-dimensional body. So you understand that when this plane cuts it, This is what we want to do. We want to isolate the left hand side part of it. Furthermore, we would like to depict a system of forces externally applied on this three-dimensional body. Some arbitrary system of forces. Now, when we are considering that one, we will only have this force and this force left. The other forces do not get depicted because we are not even considering that right hand side part of the, of course you understand that this is very much an imaginary cut. Alright. Now, when we expose this surface, you understand that if to begin with this entire three-dimensional body was in static equilibrium, this portion as I have drawn it will no longer be in static equilibrium. So, in order to have the static equilibrium maintained, I would necessarily have a distribution of forces present on this exposed surface. Now, I do not want to depict all of that. What I want to do is, I want to focus my attention entirely on this point Q. In fact, I will consider a little area, a very small area around this point Q. And now what I will say is that at this point Q, there will be a resultant force depicted through this yellow colored arrow. Now, very important to note is that it may seem apparently that this is now in static equilibrium. No, it is not. This yellow colored arrow, despite representing a force, is not balancing these forces. It may look like that, but it is not, because you note that this yellow colored arrow is only representing a force because we are considering this point Q. Had we chosen another point Q here, another point Q here, we would have different forces present those, and the entire distribution of those forces exposed on this surface, that would be balancing this external force. So, this is not in static equilibrium right now, but we want to investigate that yellow colored force. Alright, so what we want to do first of all is we want to take a component of this yellow colored force along the x direction, and we are also going to take a component of that yellow colored force along this plane or along this exposed plane. So, the picture is going to look somewhat like this. If I say that all these forces are named like P1, P2, P3, P4, P5, what I have here is just P1, P2 and P3. This one, let us call this as R, and the component, this one, the horizontal component parallel to the x direction, that will be R superscript x. Furthermore, this component which is contiguous with this plane, that will be represented by V superscript x. Please note, and I emphasize this time and again, that this Vx is not parallel to the y axis, it is neither parallel to the z axis, it is just lying on that plane. Now, if that is so, we can choose to take components of Vx along the y direction and the z direction. So, let us try to do that. Okay. So what we have at the end of all this complicated diagram is that this force R present at the point Q has been resolved into a component Rx, which is actually parallel to the x direction. This vertical component, which we call Vx subscript y, and this component Vx subscript z. So this Vx subscript y is parallel to the y direction, this is parallel to the z direction. The significance of the superscript x here, as you may have already figured out, is that it represents force components of an internal force R on such a plane on which the outward normal is parallel to the x direction. I repeat, the superscript x represents the outward normal direction of the plane that we are considering here. So this is the plane, the outward normal to it is along the x direction. It is that outward normal direction which is represented by this x, and it is present in all the things. It has nothing to do with the direction along which the force components have been taken. Now if we appreciate this, then immediately we can do something. What we can do is, we can recognize that this little area element, we'll call that as A, and we can take three different sorts of limits. So limit A tends to 0, Rx divided by A. We can take a limit A tends to 0, so basically we are taking the ratio of the force components of the original force R along the various directions, and we are dividing by the and we are taking the ratio with this area A, and we are letting this area A tend to 0. Now what we say is that as this area tends to 0, this will give me a finite scalar value, and that will be represented by this symbol. This is the Greek symbol sigma, subscript x, x. This one will be represented by sigma xy, and this one will be represented by sigma xz. You please note that all this x present in the superscript have gone to the first subscript index. The first subscript index here is x, it is x here, and it is x here. Now traditionally, in most of the mechanics of materials or mechanics of solids textbooks, what is done is, instead of this sigma xy, it is sometimes written as tau xy. Please note that this could also be written as tau xx, but generally it is not written. We identify that this is the shear, this is also the shear. So all of them are referred to as stress components. These two are referred to as the shear stress components, whereas this is referred to as the normal stress component. Now, at the end of all this discussion, we have to remember that these three definitions, it only pertains to our particular choice of the plane that we have taken. So this plane, to begin with, was made parallel or was chosen parallel to the YZ plane. Had we taken a different sort of plane, for example, if we had taken our pink colored cutting plane to be parallel to the XZ plane, suppose, then it would have been a flat cut through this, and would have also taken it to pass through Q. In that case, another kind of yellow colored R vector or R force would have been exposed, and we would have obtained a different three sets of stress components. Similarly, if we had taken another pink colored cutting plane parallel to the XY plane, so flush with the green board here, then we would have again obtained 3 different stress components. So, all in all we would obtain 9 different stress components. Now, I believe that in certain sections this part of the discussion has already been done. Nevertheless, considering the importance of all this, we are revising it again. So, let us go forward and actually write down all the stress components quickly. So, we understand that in addition to sigma xx, sigma xy and sigma xz, we would also have sigma yy, sigma yx, sigma yz, sigma zz, sigma zx and sigma zy. All right. Before going forward, we already have 2 professors sitting here, Professor Gautam Chakraborty and Professor Manas Laha, and we also have the coordinator of the mechanics course, Professor Arun Kumar Shamuntaray. So, let me just confer with them. So, in your sections, has this thing been covered, that sigma xy is equal to sigma yx, sigma yz? So, okay. Okay. So, in certain sections this has not been covered, so we'll go ahead with this. Okay. So, you want to use tau for everything? Okay. For the shear stresses. Okay, no problem. Okay. So what we are going to do is, first of all, we are going to do something very standard in mechanics of materials or mechanics of solids. So, you imagine that if I am cutting this plane like this and I am cutting another plane through this cube parallel to the xz plane, and subsequently I am taking another plane parallel to the xy, then eventually I will have a situation like this if I only consider the point Q. So, this is a repetition of that plane. So, this is a plane which is parallel to the yz plane. If we take a plane which is parallel to the xz plane, it would look something like this. And finally, if we take a plane which is parallel to the xy plane, it would look something like this. Now, note that all of these 3 planes, they pass through the point Q. Now, this is a horribly complicated picture and it is not really useful to do any analysis like this, and we would really like to do some analysis and gain some further understanding. So, what is usually done is, considering this point Q, we take a cutting plane which is just to the right of it, which is just to the left of it, which is just above it, which is just below it, which is just in front of it, and which is just behind it. All in all, what we will have, instead of this complicated diagram, we would have something which is far more familiar and convenient to deal with, and we would end up with a situation like this. And you Last how many minutes?
Couple of minutes.
Last couple of minutes.
1 to 1.5 minutes.
So was this part clear? When I was speaking here?
Yes, sir.
That part was clear?
Yes, sir.
Okay. So I have been asked by the technical people here to repeat the thing. So I'll do that. So what I was saying was this, that instead of considering this kind of a complicated diagram, it is far more intuitive and convenient for the purpose of analysis if we consider planes which are parallel to the YZ, but which is just to the right of this point Q and just to the left of this point Q. Similarly, one plane which is just above it, which is just below it, and another plane which is just in front of it and just behind it. Sorry? Oh, this diagram bigger. Okay. So if we consider those kinds of 6 planes, I'm again repeating the cube here. Okay, we understand that the point Q is present here, and what we would like to do is represent the various components of stress on the different faces. So first of all, considering this thing which we have explicitly done earlier, this is the sigma xx component, the normal stress component sigma xx. This is tau xy, and this is tau xz. You please note, as I had emphasized earlier, that the first subscript in each of these 3 stress components represents the outward normal to the plane that we are considering. The second subscript represents the direction along which we are considering the stress component. So this is parallel to the x direction. This one is parallel to the y direction, and this one is parallel to the z direction. All right. In a similar fashion, if we consider this top surface, then the normal stress component here would be represented by sigma yy. We would have another component here. This is the shear stress component given by tau yx. And finally, we would have a component, a shear stress component, tau yz. You please note that just like in this surface, on this one, the outward normal is along the y direction, which is why the first subscript in each of these 3 stress components is y. Here it is y, here it is y, here it is y. And the second subscript represents the direction along which the stress component is there. So this is the direction along the y. This stress component is along the x direction, and this stress component is along the z direction. So we are following the same kind of convention of the coordinate system that we had done earlier. So this was y, this was x, and this was z. And finally, on the front surface, which is parallel to the xy plane, we would have a normal stress component projecting out of it in this fashion. This would be sigma zz. This would be tau zy, and this one would be tau zx. And again, not to bore you, but the first subscript represents the direction of the normal to the plane that we are considering. This is the plane parallel to xy, so the outward normal to it is along the z direction. that is what is represented by this first subscript, and the second subscript, this one is along the y direction, this one represents that it is parallel to the x direction, and this one represents that this is parallel to the z direction. Okay, all this is fine, but what about its the other surfaces, the other three surfaces? So for that, we'll use a different colored chalk. Let us consider this one first. On this one, I would like to first of all represent, just as I had done for the other cases, one stress component. So I want to do something like this. I would also want to write a shear stress component along the x direction and another shear stress component along the z direction. Now, how do I represent that? What do I write for that? So, first of all, this is the normal stress sigma. So, this is drawn on this bottom surface on which the outward normal is along the negative y direction. So, what we do is we write this as y direction, okay, and for the second subscript we again write this as y. Now, I will come to a discussion about this because there is a little bit of a confusion among students always about this point. Let us first complete the writing of the shear stress directions. Now, if I want to write the shear stress, let us say along the z direction, what do I do? Can I draw a shear stress like this, or should I draw a shear stress like this? What do I do? So, what we do in general is to follow some sort of a positivity convention. So, a very useful trick that I personally use is something like this. I consider a plane and consider the outward normal direction to it. Suppose I am considering the normal one. For this, I put two blank spaces. I do not have to actually write them down, but this is only for my own understanding. Here, although I wrote this as y, but I actually recognize that this was the direction along the minus y. So, I actually write the minus y here, and I want to write the stress component projecting out of it. So, that is like minus y. So, together it is as if the minus and minus is just giving me this kind of nice positive thing. It is a positivity convention. Then can I borrow that kind of an idea to represent in a positive kind of fashion the shear stress component? I can actually do that. So, what do I do? I write my tau because I want to represent my shear. Again, two blank spaces. Now, in the first blank space, I am supposed to put down the correct sense of the direction. So, again, just like before, I will put the minus y. Now, I want to preserve the positivity of this. So, I should maintain, if I want to write it along parallel to the z direction, I should be writing it minus z. That would preserve the positivity of it, and I would be able to write this as tau yz. Now, really what I have done is I have depicted this shear stress along the minus z direction. Now, that solves our problem immediately, because here I had two choices along the positive z direction, along the negative z direction. What I can do by following my positivity convention is to avoid all confusion and write this directly as tau yz. Next, following a similar sort of idea, I can write down my tau yx like this. Because you understand that in place of this z, I can just write an x, and that will give me tau yx with a positive sense. So, this is what I have. You please note that this tau yx that I have written here is opposite to this tau yx. All right. What about this one? So, if I consider this plane. Now, because I have already cluttered the whole diagram, let me erase a few things. Okay. Now, my yellow colored surface is nicely highlighted. Again, I can immediately write down my normal stress component like this. This is my sigma xx. So, the first one is like minus x, the second subscript is like minus x. Next, for my shear stress component, which is parallel to the y direction, I understand that this time I have to use the first one is minus x, the second is minus y. So, this one represents the correct sense of direction of the shear stress. So, here the correct sense of the for this plane, the correct sense of direction of the shear stress parallel to the y direction would be along the negative y direction. So, what I need to depict it is like this. So, this is tau xy, and you note that this tau xy direction is opposite to what I have here, and in exactly the same fashion I can write down my tau xz. And again you note that this sense is along the negative z direction, opposite to this one. And finally, for the surface which is behind it, so to highlight it, if I consider this plane and I erase everything else to remove the clutter, the normal stress would be along the negative z direction. So, that goes behind. So, this is my sigma zz. The shear stress which is parallel to the y direction would be oriented along the negative negative y direction. So, this is what I have, tau zy, to maintain the positivity of the overall thing. And finally, this is my tau zx. So, again you note that this yellow colored surface, the outward normal to it is along the negative z direction. So, that represents that means that we have a minus z here, and together we have a minus x here. So, this direction is along the negative x direction. All right. So, if we have these ideas clear, then we can go forward and discuss something very important, which will be immediately relevant for our actual intended purpose of discussing the transformation of stresses. So, what is that? We have understood, got an idea about all the stress components, but suppose we ask ourselves that to begin with, if we come back here, suppose we consider the same three-dimensional body, suppose we consider the same set of P1, P2, P4, P5 forces, but we take a different sort of cutting plane, meaning that instead of this XYZ coordinate system, suppose we choose something else. Suppose we take yes. So, so this new kind of axis that I have drawn here, that I will depict by x dash, y dash, z dash. Now, you understand that x dash, y dash and z dash is a perfectly valid rectangular Cartesian coordinate system. Now, if I were to begin the entire story all over again, then what I would do? I would consider a plane which is parallel to this y dash z dash plane, and I would take a cut like this that would expose a surface like this, and the whole story would repeat. At the end of the repetition of that whole story, what I would get is again a cube, not quite like this, but something which is a little bit tilted to it. But more importantly, what I would obtain at the end of it is a set of stress components which would be written like sigma x dash, sigma y dash, sigma z dash, and so on. Question is, in general, would they be equal? Answer is no. So, when we considered our xyz system, we ended up with sigma xx, sigma yy, and so on. When we use the x dash, y dash, z dash system, we would end up with sigma x dash, sigma y dash, and so on. In general, and this is very important, sigma xx is not going to be equal to sigma x dash, sigma yy is not going to be equal to sigma y dash, and so on and so forth. So, in general, when we choose a different sort of a different set of coordinate axes, the stress components which arise as a result of that different choice is not going to match. Now, the situation is very peculiar. You see, to begin with, we were considering the same three-dimensional situation, the same body, the same set of externally applied forces. It is just that we have chosen to take a different sort of set of coordinate axes, and we are ending up with different stress components. So, what is really going on? So, we have to really understand one very subtle point. Subtle point is that the physical situation is the same. Now, this physical situation is what is referred to as the state of stress. Now, what we are obtaining, all this complicated diagram and all this long discussion, that is just the mathematical machinery to represent this physical state of stress. The stress components that we are obtaining, I am again highlighting, is completely dependent on our initial choice of the coordinate axis, which is why when we take a different sort of coordinate axis like x dash, y dash, z dash, these things are not equal. So, on the one hand, we have the same physical system, physical situation, but by choosing different sort of coordinate axis, we are ending up with different stress components. Question is, are they really the same thing? Are they representing the same thing? Well, of course, yes, because this is just a mathematical representation of the same physical setup. How can it mean different? That means the natural conclusion is, even though they may not be equal, there must be some sort of relationship which connects this one and this one. It is not directly equal, but there is some relationship between the stress components which arise by taking different sorts of coordinate axes and by considering different sorts of cutting planes. So, when we consider the state of stress at a particular point, it really means only one physical situation in reality, but the mathematical representation of it may turn out to be different by taking different choices of the coordinate system. Now, this mathematical machinery, this mathematical connection between these different stress components can very well be established, but the important point is that in our first year mechanics syllabus, we do not have to do this entire three-dimensional complicated version. What we will do is a reduced version of this, and this is not only for the purpose of the reduced scope of first year mechanics, rather this reduced scope is very much important in real engineering practice also. So, this is referred to as the situation of plane stress, which we will cover in the next topic. Okay. So, this reduced 2D system is this special reduced 2D system that we are going to consider is the system that is usually referred to as plane stress. So, what is this plane stress system? All right. In general, we have seen that we have the various stress components sigma xx, sigma yy, sigma zz, sigma xy, sigma yz, sigma zx. But when we are considering plane stress, what we do is we say that sigma yz is equal to 0, sigma zx is equal to 0 and sigma zz is equal to 0. So, what we are actually doing? What we are actually doing is considering a physical situation like this. Now, what is this? This is not a general 3-dimensional body, it is still a 3-dimensional body, but of a special kind of shape. So, this is only one instance of a plane stress example, but it will help us to concretize our ideas if we look at this example. So, this is like a general shaped plate. This thickness is very small compared to the lateral dimensions of this plate. This thickness is very small. This is like a dish. Okay. Furthermore, the loading that will be applied on this kind of a body is also not general, rather it will be limited to act only in the plane of this thing. So, maybe only along something like that. As a result, what we will have is sigma zz equal to 0, sigma yz is equal to 0 and sigma zx is equal to 0. Please note that in general sigma xx is not equal to 0, sigma yy is not equal to 0 and sigma xy is not equal to 0. So, this kind of a system whenever we have, it is referred to as a state of plane stress. All right. So, why are we actually discussing this? So, just like as we had considered a point Q within this within a 3-dimensional body, we will again consider a point Q, but this time we will start looking at the entire picture from the top down. So, this kind of a thing will start to look like this. So, this is the top view of it, where this point Q is an arbitrary point Q chosen somewhere within this. Yes. Yeah, sure. Yeah, because we have not discussed that. Okay. So this is some point Q here. Now, just as we had considered the cube around that point Q, we can consider a small area around this. We understand that although in this top down view, this is looking like a little square, but actually this square has a very small thickness into the plane of the board. Now, going back to our previous discussions, here also we can set up our coordinate axis like this. This is x and this is y. Now, as we had discussed earlier, what happens if we considered the same diagram, the same point Q inside it, but consider a different sort of coordinate axis like this. Suppose this is x dash and this is y dash. Here you note that I would have to draw my little element like this. This is still the point Q. Now, in this diagram, you understand that I have my sigma xx not equal to 0, sigma yy not equal to 0 and sigma xy not equal to 0. So, if I zoom into this little element, I would have a picture like this, and here I would have a picture something like this. And again, tying with whatever we had discussed in our 3-dimensional case, here also, even though sigma zz is not there, sigma yz is not there, sigma zy is not there and sigma zx is not there, and please note that going by our previous convention, in most textbooks you would find it in terms of tau. Our question is, what, if any, is the connection between the various stress components that I have written down here and the various stress components that I have written down here? How can I find that out? Oh, sorry. Thank you. So, this is my tau xy. Okay. How can I find out the relationship between them? All right. Now, even before we get into that question, we have to answer something very important. This tau xy, does it have any connection with this tau yx? How can you find it out? Similarly, we can ask the same question if there is any relationship between tau x dash y dash and tau y dash x dash. Okay. So, what we will do is, I believe this was not covered in, I will proceed with this, right? Okay. Okay, we want to ask two questions. First of all, what is the relationship between tau xy and tau yx, or equivalently, what is the relationship between tau x dash y dash and tau y dash x dash? And second, and this is the second relationship that I am going to ask, it will directly be the topic of discussion of that heading, transformation of stresses. So, what is the relationship between sigma xx, sigma yy, tau xy, this entire thing what is that relationship Please note that when I am asking this question, I am not making it a point to write separately about tau yx and tau y dash x dash, because I am already assuming that I have answered this question. So, first of all, I will try to answer this question and then go on to this. Okay. So, we want to answer this first question here. What we will do is, we will consider, so we have already mentioned that this is a little square, and let us consider that each of the sides of this square is of length twice a. So, this is twice a and this is twice a. Okay. Now, what I want to do is I will consider the moment let me consider the moment about an axis which is passing through the center of this square. So, since I have already named that point as Q, now this condition follows from whatever we have learnt in the first part of our mechanics course in the pre-mid semester portion, that this is a little element which is in static equilibrium. This is a two-dimensional situation, effectively a two-dimensional situation. So, we must have that sigma fx is equal to 0, sigma fy is equal to 0, and the moment about a wisely chosen axis should be equal to 0. So, if we try to find out the moment, what do we get? Now you note that when I am considering this kind of a little square, which usually is referred to as a stress element, we might as well have called it something else, but we all call it as a stress element. Nowhere here we are actually depicting a force, but you understand that each of these stress components is actually obtained by considering the limit of a force with a particular area. Now just as I can obtain this shear stress, for example, from a force, so also I can obtain the force back from it. So how do I do that? So I will consider one by one the force which is contributed by this tau xy. I will consider the force which is contributed by this tau xy. I will consider next the force which is contributed by this tau yx, and I will consider the force which is contributed by this tau yx. Please note that for the purpose of calculation of this moment about the point Q, I do not have to consider the contributions from the forces due to sigma xx here, this sigma xx here, this sigma yy here, and this sigma yy here, because as depicted, those forces would be passing through this point. So they have zero moment arms. So now considering, let me just quickly name these vertices. So let's say this is A, B, C, and D. Considering the face BC. Now when I say the face BC, it actually means the edge BC together with the little thickness that is going into the plane of the board. So the area of that face BC, it will be depicted by A, so tau xy times A. So area, A is the area of each face represented by the edges AB, BC, CD and DA. They are all of equal length. The thickness into the plane of the board is the same all throughout, therefore they have the same area. So I don't have to worry. So tau xy times A represents the force which is contributed by this upward pointing shear stress tau xy, and the moment arm from here is how much? This entire length is twice A, half of this is A. So that will be A. What is the sense of this? We take the arm like this and we use our right hand thumb rule. So this is having the sense counterclockwise. For our problem, we will take the counterclockwise as positive, depicted like this. Next, let us consider the force which is contributed by this AD edge or AD face. I will write the minus or plus later on. Let me first write down the force component. This is tau xy times the same area A, but this A now represents the area of AD. This one has a moment arm about Q which is equal to A again. And what is the sense of this? This is the moment arm. Again, using the right hand thumb rule, it curls in the counterclockwise direction. So by our convention, this is positive. Now next we consider the upper face AB. There the force is contributed by this tau yx. So we write that down, tau yx. Please note that I am writing this in the same line. Okay, so this is like a dot dot dot. So this is in the same line. I have just run out of space there, so I am continuing here. So tau yx times A. So this force is directed left to right, the moment arm is this much A, and again it is curling like this. So, that curling sense is in the clockwise direction. So, it is curling like this. So, this is minus. Again I highlight this point that I have, for my convention, I have taken the counterclockwise as positive. This turns out to be clockwise. So, this is negative. Finally, I consider this edge CD. Here I have tau yx again multiplied by the area A. The moment arm about Q is A, and I confirm that if I curl my fingers, it is again in the clockwise direction, which means that I need to put a minus sign here. This entire thing is equal to 0. Now, at one shot we can find out the neat relationship that tau xy is equal to tau yx, because all the capital A's, the areas are common, the small a's are common. What we will have here is twice of tau xy is equal to twice of yx. So, finally, tau xy is equal to tau yx. This is a very, very important relationship. Now, you note that this directly answers this question, that tau yx, there is no more a question mark here, rather we have answered it directly by saying that this is equal to tau xy is equal to tau yx. Now, you note that I was drawing this diagram about the point Q by considering the xy coordinate system. Suppose instead I had considered my x dash y dash coordinate system. Within that coordinate system also I would have been able to draw a square, and if I proceed exactly like this, I would have ended up with tau x dash y dash is equal to tau y dash x dash. I believe there should not be any confusion about that. So, this answers this question also. Yes. So, our course coordinator Professor Samantara has just mentioned that this is a very, very nice time to also highlight the important fact that just by considering this reduced two-dimensional system, just as we had found out that tau xy is equal to tau yx, so also we will be able to show very, very neatly that okay, because we have these two things to be equal, what we really end up with is that if we go back to the different components of stress that we had obtained earlier and we quickly write them down. So, sigma xx, sigma yy, sigma zz, tau xy, tau yx, tau zx, tau xz, tau yz, tau zy. We understand that these two are the same things. These two are the same things, and these two are the same things. So, effectively what we can conclude from here is that at a point referred to a particular coordinate system, what we have really is a state of stress represented mathematically by 6 independent components of stress. So, even though we, in terms of representing, we found out that we had 1, 2, 3, 4, 5, 6, 7, 8 and 9 components showing up, but through this exercise we have found out that effectively we end up with 6 independent components of stress. And while we are doing the maths of it, let me just tell you that usually this general state of stress in a particular coordinate system, and using all this information that we have just learned, is usually written in terms of a 3 by 3 matrix in this form: sigma xx, sigma xy, sigma xz. Oh, sorry. We will follow the usual convention of writing it as tau, tau xy, tau xz, tau xy, sigma yy, tau yz, tau xz, tau yz, sigma zz. So, this representation, it is sometimes referred to as the state of stress represented like a stress tensor, but you do not have to keep on discussing all of that. Let us go back to our original question. Okay. So, as a result of this, what we can say is that when we were drawing our cube, we ended up with a very, very complicated picture. So, just to remind you, I will borrow a little space from here. So, when we drew this 3-dimensional picture, we ended up with quite a cluttered representation where we had to write all the 9 components of stress, but that is no longer necessary because refer to this particular coordinate system x, y and z, we can very clearly just write sigma xx here, tau xy here, tau xz here, considering the actual phase which is having the outward normal along the positive x direction. Similarly, I can just write it as sigma yy Please note that just like before, I have written this as tau zy, but this is no longer necessary. I can write this in terms of tau yz directly. And the final shear stress component tau zx, this is what I had written earlier, but again I need not distinguish between tau zx and tau xz, and I can write it simply like tau xz. Okay. In the time that we have left, let us try to answer this question, whether or what relationship exists between these 3 components of stress considering the xyz system and these 3 components of stress considering the x dash y dash z dash system. And here you note that it really makes sense for us to consider only these 3 stress components, because we have already established in the previous question that tau xy is very much equal to tau yx and tau x dash y dash is very much equal to tau y dash x dash. So we only have to establish this connection. All right. So, so to answer that second question, the relationship between sigma xx, sigma yy and sigma xy with sigma x dash, sigma y dash and sigma x dash y dash, what we are really asking is what is the transformation rule between the stresses. So, we can finally start with this topic of discussion, transformation of stresses. Please note that whatever we will be discussing, it will be limited to the reduced 2D system which we are referring to as the plane stress situation. So, to quickly draw the diagram again, so this is my xy system and sorry. And this is my x dash y dash system. This is sigma xx, sigma xx, sigma yy, sigma yy, tau xy, tau xy again. I again emphasize that I am no longer writing this top shear stress as tau yx, rather I am using the relationship that tau xy is equal to tau yx. In a similar fashion here, what I will obtain is sigma x dash, sigma x dash, sigma y dash, sigma y dash, tau x dash y dash, tau x dash y dash, tau x dash y dash and tau x dash y dash. Okay. Now, in order to find out the relationship between these two sets, the strategy that we will be following will be effectively in spirit exactly the same as the one that we had utilized in finding out the relationship that existed between tau xy and tau yx. Basically, we would be considering the static equilibrium of a shape which is centered around this point Q. So, when we were considering the question of establishing the relationship between tau xy and tau yx, we considered this particular stress element because the entire story was devoted to this picture. Here, however, the story is sort of trying to establish a bridge between this one and this one. This point Q is the same point Q here. It is only that this edge is vertical here, whereas this edge is oblique here. So, perhaps if we can draw one single diagram in which we can show both these kinds of vertical and horizontal edges and that kind of an oblique edge, perhaps we can think, or we can give it a shot and attempt to find out some sort of a relationship between them. So, towards that end, let us try to draw a special kind of diagram. So, it is nothing, it is not rocket science. So, this is just the point Q. We are just doing a little clever arrangement like this. So, this vertical edge is very much like this vertical edge that is parallel to the y direction. This horizontal edge is very much like this horizontal edge which is parallel to the x direction, but here I am choosing not to complete this square. Rather, what I will do is, to complete this diagram, I will take an edge which is parallel to this edge. So, perhaps it will be better if I use different colors. So, this is from the pink colored XY system. So, this thing, and from that blue colored system I will have this kind of a edge. Okay. Now, we can quickly write down the various stress components which will be shown on this sort of diagram. We understand first of all that just as we had sigma xx and tau xy present, we will also have a sigma xx here and a tau xy here. On this horizontal edge, we will have the sigma yy and this shear stress component tau xy, and on this oblique blue edge we will have faithfully obtaining from here so all right. So, our initial question was, what is the connection between sigma xx, sigma yy, tau xy and sigma x dash, tau x dash, y dash and sigma yy. Now, in this sort of a diagram, we have almost achieved what we want to obtain, but in the process we have lost something. That loss is that nowhere in this diagram this sigma y dash is appearing, but not to worry. Through a little clever trick at the very end, I will be able to obtain the relationship. So, using the static equilibrium of this picture, I should be able to obtain the relationship between sigma x dash and these things and the tau x dash y dash and these things. And as I have already mentioned, that the strategy that I will follow is again to consider the static equilibrium of this thing. So, what should I do? In which direction should I obtain the static equilibrium? Well, as I have already mentioned, I want to express my sigma x dash in terms of these things, and next I want to obtain the tau x dash y dash in terms of these things. So, the clever idea here is that we will consider the static equilibrium of sigma f x dash is equal to 0 and sigma f y dash equal to 0. Basically, we are going to consider the x dash and the y dash directions. So, first of all, okay. Now, just as we had done earlier, we are going to consider the various force contributions from these stress components, from this one, from this one, from this one, all of them. First of all, we are going to consider the x dash direction. So, let us be very clear about what we want to do here. For the purpose of clarity, let me erase whatever I don't need from here. Let me erase this thing. Let me erase this also. Sorry? No, it's coming. Okay. Now you see, my choice here is to consider the static equilibrium along this x direction, the force equilibrium along this x dash direction. Now, when I am saying that I want to find out this relationship, what is one thing which is given to me? The one thing which I really know is what is the relative orientation between the x dash y dash axis and the xy axis. So, perhaps it will be useful for us if we can actually explicitly represent those two axes in this diagram. So, what I will do is, here you note that this blue one corresponded to my blue x dash y dash direction. So, this blue one is my x dash direction, this is my y dash direction. The red one corresponded to the red xy direction. So, this one is x and this one is y. The one piece of information which I absolutely know is the angle that x dash makes with x. That is something which is given to us. So, we know this theta. If we know this theta, you immediately understand that this is also theta. And if that is theta, this will be also theta. Okay. Now, in order to make my life a little bit easier, wherever I will have the complement of theta, that is 90 degree minus theta, I will represent it like this by a double curved arrow, by a double curve. Okay. So, first of all, I want to do that sigma fx dash equal to 0. For that purpose, what I will do is, I will one by one consider these three edges. Perhaps it will be easier for me if I name them just as I had named the vertices earlier. So, I will call them L, M and N. Okay. Now, earlier I had the luxury of considering a very nice neat geometrical figure like a square. Here this is LM, this is MN, but this is an oblique thing. So, it is not very convenient, but we can get around the difficulty. So, what we will say is that this face represented by the edge Ln, let this have the area A. The moment we understand that, we can immediately write that Lm, the face which is represented by the edge Lm, will have the area A cos theta. This is A, this will be A cos theta. And finally, this face represented by the edge Mn, it will have the area A sin theta. Okay. Why do we need that? We need that because in order to go from these stress components to the forces, I would need to multiply by the appropriate area. That is the whole motivation of considering this. So, first of all, I will consider my face represented by the edge Lm. First, I will consider the force contributed by sigma xx. Let me write that down. Without any bias about the positivity or negativity, I will just write down the force and then I will worry about the sign. So, sigma xx is the stress component. In order to obtain the force, I need to multiply with the appropriate area. Area here, just by referring quickly to this, is A cos theta. Now, our job is not yet done because you remember that our motivation here is to take the force equilibrium along the x dash direction. This force as represented is along the negative x direction. So, we need to take the proper component of that force. So, what is the proper component of that force? We have to consider a direction which is parallel to this x dash direction. It is oblique like this, oriented at angle theta with the horizontal. I have to tilt a straight line like this and write this as my theta. So, this is theta, these are vertically opposite angles. So, the force component contributed by sigma xx will have to be taken along this direction, and because this is tilted at theta to the horizontal, I will further need to multiply this force by a cos theta. But our job is not yet done, because we have chosen till now not to worry about the positivity or negativity of it. You see, we are considering the force contribution or the force equilibrium along the x dash direction. Implicit within it is that the x dash direction will be considered to be positive. You see, what is the direction of this force? It is along the negative x dash direction. So, we should put a negative sign here. All right. So, only one stress component is done. So, next we will consider this tau xy contribution. Again, without bias or without worrying about the positivity or negativity, we will write down the tau xy. We have to multiply first of all by the corresponding area, that is the Lm, and that is again a cos theta. No worries till this. But now again I have to consider the force component contributed by this tau xy along the negative x dash direction. So, what I have to do is I have to take the force contribution again along this direction. Now, you understand that this angle is the complement of theta. So, this is depicted by this double thing. So, this is equal to this, which is equal to 90 degree minus theta. So, if I take the cos of 90 degree minus theta, I end up with sin theta. And finally, I have to worry about the sign, and you note that this one is along the negative x dash direction. So, I have to put a negative sign here. So, the face represented by the edge Lm is now done. Next, we move on to the face represented by this edge Mn. First of all, we will consider the force contributed by this sigma yy. That has to be multiplied by the proper area. Mn, you note here, is given by a sin theta. So, we write that down. Next, we have to again take the component of the force contributed by this downward pointing stress component along the x dash or parallel to the x dash direction. We draw a dashed line which is parallel to the x dash direction, and just by comparing with this particular case, we can immediately identify that this angle is also going to be 90 degree minus theta. So, what we need to write here is cos of 90 degree minus theta, which is nothing but sin theta. And finally, you note that this is pointing downward. When we take the component of it along this dashed line, this is along the minus x dash direction or the negative x dash direction. So, we need to put a minus sign here. Next, we will consider this tau xy, which is pointing from right to left. Tau xy multiplied with the area of that face represented by Mn is nothing but a sin theta, and what we have to do is take the component of this one along a direction which is parallel to x dash. So, you see, this is 90 degree minus theta, this is the complement of 90 degree minus theta. So, that basically comes out as theta. So what we can write here is directly cos of theta. And finally, this when we are taking the component of this along this dashed line, it is again along the negative x direction, x dash direction. So this is coming with a minus. So we have written down the various force components considering Lm and Mn, but we have not yet considered this Ln edge. So let us write down that. For Ln, what do you think should be the correct force contribution? Will it be contributed by this sigma x dash x dash? So let me highlight this here. We have one force component from this sigma x dash, and we have another force component contributed from this tau x dash y dash direction. So when we are considering along the x dash direction, surely it is the force from this normal stress component which is going to be the relevant one. So sigma x dash is the relevant stress component that has to be multiplied by the proper area. We are considering the edge Ln, the face represented by the edge Ln, that has the area A. Now you note quickly that unlike all the previous cases where you had to take the proper component, but this one, this sigma x dash by definition is along the x dash direction. So there is no need to take any component. The entire contribution is perfectly all along the x dash direction. So and also the sign is positive because you know that this arrow is pointing perfectly along the x dash direction. Okay, our job is almost done. Here you note that in each of the terms the capital A area is coming as common. So with a little bit of algebra we can quickly write this as sigma x dash is equal to, what we do in the next step is we cancel A and we transpose each of these terms which are coming with a minus sign to the right hand side. So effectively what will end up is sigma xx cos square theta plus sigma yy sin square theta, and you note here this is a tau xy cos theta sin theta and here it is a tau xy sin theta cos theta. So effectively what we have is plus twice tau xy sin theta cos theta. Okay. Now it is very much possible to convert this to cos 2 theta, sin 2 theta and so on and so forth, but we will take care of that later. First of all, what we want to do is, just like we have been considering the sigma f x dash equal to 0, next we will consider the sigma f y dash is equal to 0, and our hope is that that will give us some sort of relationship between this stress component tau x dash y dash with the other things. So let us check that. So people who are watching this and following along by taking notes, I would urge you to number this equation as equation 1. We will refer back to this equation 1 later. Next we are going to consider sigma f y dash is equal to 0. Okay. The first thing that we need to do is remove all this clutter. you note that I really do not need to erase anything here. Okay. So for sigma f y dash equal to 0, just like earlier, I had started by considering the face represented by this edge Lm, and I had started really by considering the force contributed by sigma xx. I will do the same thing here. Again, without worrying about the plus or the minus, let me write down the force contribution. Sigma xx will be multiplied by a cos theta, referring to this one, Lm is a cos theta. But this time I have to take the force component not parallel to the x dash direction, rather parallel to the y dash direction. So I highlight it once more that this time we are considering the force balance along this y dash direction, this one. Okay. So if that is so, I need to draw a dashed line in the spirit of my earlier exercise in this direction. Okay. So you note quickly that if this is theta, this angle will also be theta, and this will be 90 degree minus theta. Okay. So what I am doing is I am taking a cos of 90 degree minus theta, which is nothing but sin theta. Furthermore, you note that this force component taken along this direction is very much pointing along the positive y dash direction. So it is coming out with a positive sign. All right. Next, I am again going to consider the edge Lm, but this time the force contributed by tau xy. Tau xy will be multiplied by a cos theta, and now I have to take the component along parallel to the y dash direction. So parallel to the y dash direction would be something like this, and this angle is very much theta. However, when we take the force component of this tau xy along this dash direction, it comes out to be opposite to the y dash direction, that is along the negative y dash direction. So it comes with a minus sign. Next, we consider the face represented by Mn, and first of all we consider the force contributed by sigma yy. The area of this face represented by Mn is a sin theta, and again I have to take the component of that force represented by this sigma contributed by this sigma yy along the y dash direction. So again, comparing with this particular case, this angle is nothing but theta. So all I have to do is consider the cos theta. This force along this dash direction is along the negative y dash direction. So this is coming with a minus sign, and next I have to consider the force contributed by this tau xy. So tau xy will be again multiplied by a sin theta, and I have to take the force component of the force contributed by tau xy along the y dash direction. So drawing a dash line along the y dash direction, I understand that it is this situation is exactly like this corner at n, which means that this angle is nothing but 90 degree minus theta. So here what I will have to write is cos of 90 degree minus theta, so that is a sin theta. This one, this force component along this will be oriented along the positive y dash direction, so this is coming with a plus sign. And finally, just like before, I should not be forgetting my edge Ln, the face represented by Ln, and this time you note that there will be no force contribution due to the stress component sigma x dash x dash. The entire force along the y dash direction will be solely and solely contributed by the tau x dash y dash, and that is very much along the positive direction. So, very quickly we can write that tau x dash y dash multiplied by the appropriate area, which is of Ln, that is just A, and the entire component or the entire force is along the y dash direction, is along the positive y dash direction. So, it comes with a positive sign, and that should be equal to 0. All right. Again, just like before, the capital A cancels out from all the terms. On the left hand side, I keep my tau x dash y dash and I transpose all the remaining terms to the right hand side. So, what I will obtain is that this one will become a minus, this one will become a plus, this one will become a minus, and this one become a plus. But more importantly, there is a certain pattern which is emerging here. You see, the sigma xx comes with cos theta sin theta, the sigma yy also comes with cos theta sin theta. The tau xy terms also have a nice thing going on here, which is it is multiplied with cos square theta, and this one is multiplied with sin square theta. So, if we skip a few steps, can we not write something like this? So, you please check, this plus becomes a minus sigma xx sin theta cos theta. On the right hand side, I have a minus minus plus of sigma yy, and this was actually a minus here. So, this is very much correct. Next, for the tau xy term, all that I need to do is write it like tau xy, taking that as common. What I will obtain as its coefficient is cos square theta minus of sin square theta. Okay. Just like I had mentioned in passing in the previous case, when considering the sigma f x dash is equal to 0, that I can very much convert these things to sin 2 theta and cos 2 theta, but I will resist that temptation right now, and I will just write that as 2. Now, it is time to do some algebraic manipulations and see what we can obtain. What I have written down here is just a rewrite of the equation number 1 that I had written earlier. This I rewrite in turn. This time I actually write this as, I convert this to my cos 2 theta, and this one I convert this to again to cos 2 theta. So, using trigonometric identities from our high school, this cos square theta will be, so we just remind ourselves that we are going to use this thing, that cos square theta minus sin square theta is equal to cos 2 theta. So, that gives me twice of cos square theta minus 1 is equal to cos 2 theta, or 1 minus 2 sin square theta is equal to cos 2 theta. So, you may consider this as a little bit of rough work. So when I use this first of these relationships, the cos square theta becomes 1 plus cos 2 theta divided by 2. This one becomes, from the second of these relationships, that, and finally the 2 is already present, which just needs to be written with these things to, so we can quickly write that as tau xy sine 2 theta. Let me erase this little bit of rough work that I have used. So my sigma x dash is equal to, now what I will do is, you see that I have a cos 2 theta here, I have a cos 2 theta here, I will take those two things as common, and if I do that, I very nicely obtain a half of sigma xx and a half of sigma yy together. So I write them down. Next, I write this half of sigma xx minus the sigma yy multiplied by the cos 2 theta. And let us not forget that last bit, tau xy sine 2 theta. Okay. Now, in the little portion that I have remaining left in this board, I want to utilize this equation number 2 to convert it directly in terms of sine 2 theta and cos 2 theta. And that I can do very nicely by noting that this sine theta cos theta is basically sine 2 theta by 2, and this cos square theta minus sine square theta is nothing but cos 2 theta itself. So and this one is nothing but the first one gives me the relationship that I was seeking initially between sigma x dash referred to the x dash y dash z dash system to sigma xx, sigma yy and tau xy referred to the xyz coordinate system, and here I have the relationship that I was seeking between tau x dash y dash and sigma xx, sigma yy and tau xy. So I will number this equation as equation number 3 and this final equation as equation number 4. Now, because we have almost run out of time, what I would need to do next is to note that in this diagram, as I had noted earlier, I do not have anything to do with sigma y dash, but can I perhaps find out the sigma y dash by some sort of insightful understanding by looking at this sigma x dash. So should I continue? I'll finish that. Okay. So we quickly note that. So let me erase all these things. For my sigma y dash, I just have to note that if I go back to my picture like this, I had my sigma x dash here, and my sigma y dash here. So it is as if this sigma y dash is just a different version of this particular normal stress component sigma x dash rotated from here to here counterclockwise by 90 degrees. So the little trick which we will use is we can obtain the answer for sigma y dash by just adding onto this thing 90 degrees. So what we will do is we will say that to obtain the expression of sigma y dash we just need to substitute theta by theta plus 90 degree in the expression of sigma x dash. So if we do that, what we obtain is sigma y dash is equal to, if we substitute here, the first term remains as it is. The second term, it becomes this is cos 2 theta plus 180 degrees, and finally for the third term I have tau xy sin 2 theta plus 180 degrees. So finally that will give me half of sigma xx plus sigma yy. Now you note that cos 2 theta plus 180, considering all those tricks that we learned in high school trigonometry, that will be in the third quadrant. So that will be basically with a negative sign. So cos of 2 theta plus 180 is basically minus cos 2 theta, and similarly in the third quadrant we also have the negative sign. So this will be my equation 5. All right. So with that we conclude this first session of the special mechanics class. Thank you very much. Okay. Next class. Okay. So Professor Manas Laha has pointed out that if we just add the equation number 3 to the equation number 5, what we will obtain, so it is very easy to see, we can do it in 10 seconds. So you see this is a half of sigma xx plus sigma yy, and this is a half sigma xx plus sigma yy. That gives me sigma xx plus sigma yy, and this minus cancels with this plus, and this minus cancels with this plus. So that is basically the end there. So this nice relationship comes out that no matter which kind of or what orientation of the coordinate axis we choose, the summation of the normal stress components sigma x dash plus sigma y dash will always be equal to the summation of the normal stress components in another coordinate system. Please note that this does not at all mean that sigma x dash will be equal to sigma xx, nothing like that. It just so happens that this particular summation has this special form of being equal to this, and this particular property is referred to as stress invariance. So just like we have this particular property of stress invariance, we can have other versions of stress invariance. So we'll see them as we go along. Okay, thank you very much. Oh, is anyone asking any question? Is anyone left? 2 students are left.